man, Temple got crushed, and man, did Green Bay whoop us. Oh, man, that was a disaster. Jeez. Rodgers, you give him two extra seconds in the backfield, he's going to kill you. They had no defensive rush at all. All right. Did Peter go over any inductor problems, or what problems did he go over on Wednesday?
He went over 9-TAC-27, which used sines and cosines.
Okay. All right, so where I left it off last Monday, we were doing this little induction coil, and the relationship for the induction coil is, again, it's similar to the capacitance, but in this case, the voltage is equal to the induction coil, the value of the induction coil times the derivative of the current going through it. So the voltage across it is equal to the inductance itself times the rate of change of the current through the inductor with respect to time. Okay? All right, so the again, once we solve for the current, we have 1 over L, the integral of, again, some initial time point to some final time t of the voltage across the inductor plus the initial current. So it's very similar to what we had for capacitance. Capacitance, we had V of t is equal to 1 over C, the integral of the inductor current, of the capacitor current plus an initial voltage. So it's very similar. All right, and this is what we're going to exercise today. And then the power is just 1/2 the inductance times the square of the current through it. Okay? And I showed you some videos. So this summarizes, this one slide on your blackboard summarizes the circuit element, which is a resistor, Ohm's law, V equals IR, the current is equal to V over R, and the power is equal to the product of the voltage times the current. For an induction coil, the voltage is equal to the inductor times the rate of change of the current, and hence the current. When you solve for this, for the current, you get the little integral there, and then the power is just that. And again, and for the capacitor, the units are farads. The voltage relationship is 1 over C, the integral of I dt plus a constant, and then the current is C dV dt, and then the power is just, again, 1/2 CV squared. All right, so now let's look at a problem where we're now going to have 12 millihenry inductor, and the current through it happens to be I of t. So I of t is equal to 30 e to the minus 2t. And this is valid for t greater than or equal to 0. And what we're asked to find is the voltage across the inductor. Yeah. 30T. Thank you, sir. Okay? So it's 30T e to the minus 2t. All right, so now what we want to do is determine the voltage across the inductor, V of t. V of t is equal to, again, L di of t dt. Okay? Now, so what we want to do is we have to differentiate the current. So now what we have is V of t is equal to L, which again, this inductor is a 12 millihenry. So it's 12 times 10 to the minus 3. And then we have d dt of 30t e to the minus 2t. That's what we have to differentiate. Okay? We have to find that derivative. Now, if you notice here, how do you differentiate that thing? Any ideas? What kind of rule do I have to use here? All right, we're doing this. We're differentiating with respect to time F1 of t, F2 of t. What rule do you need for that? You need the product rule, okay? We have two time functions. Now, the 30, I can pull that out, all right? So here, let me pull the 30 out of here. So we have V of t is equal to 30 times 12 times 10 to the minus 3. And then we're going to be dt of t e to the minus 2t. So we're going to let f1 of t equal to t, f2 of t is equal to e to the minus 2t. Okay? Now, when we do the derivative of these two, what do we have? What's the product rule? Somebody want to pony up and let me know what the product rule is? So you're going to have f1 of t times dt of f2 of t plus f2 of t dt of f1 of t. That's our product rule. Okay? So now we're just going to apply this for these two functions. Okay? So v of t will equal to, can somebody crank out a number for me here? 30 times 12 times 10 to the minus 3 when you get a minute? Whatever that number is going to be. So now we're going to have, it's going to be f1 of t, which is t, times d dt of e to the minus 2t. And I need these brackets around here, plus e to the minus 2t of t. All right? 0.36? Thank you. So now we have v of t is equal to 0.36 times. Now, we have the t here. This is t. The derivative of e to the minus 2t. Yeah. Minus 2e to the minus 2t. So this becomes a minus 2e to the minus 2t plus e to the minus 2t. What's the derivative of t with respect to time? 1. All right, so this is equal to 0.36 times minus 2t e to the minus 2t plus e to the minus 2t. And that's what we get for v of t. Okay? Now we need to determine, determine the voltage course, determine the power being delivered to the inductor at 1 second, okay? So the power is the product of the voltage and the current. So P of T is going to equal the V of T times I of T. And V of T is 0.36 times minus 2 t e to the minus 2t plus, what was that other term? E to the minus 2t. Oh, and before I forgot last, the dean kind of yelled at me. Pass around the attendance sheet. Please print and sign your name, so I don't get yelled at again. All right, and then I have to multiply this by the current, which is 30e minus 30t e to the minus 2t. Okay? Can you guys see that over there? They're losing you? All right. Let me do it. Okay? Is that better? All right. You in the back? Do I need to write bigger?
Yeah.
A little bigger? A little bit? No problem, no problem. Hey, that's why you paid big bucks, pal. All right, so we got P of t is equal to V of t, which was 0.36 times minus 2t e to the minus 2t plus e to the minus 2t times I of t, which was 30 t e to the minus 2t. All right. Now we just now we substitute in t equals 1. And I'm going to need to get that calculator warmed up. So it's 0.36 minus 2. Now we're doing this at t equals 1. So this becomes a 1 e to the minus 2 times 1 plus e to the minus 2 times 1, 30 times 1, e to the minus 2 times 1. That's evaluating the power at t equals 1. There, he's passing back the attendance sheet to you there. Okie dokie. I think I've ran the numbers for this already. So that's what we get for the inductor voltage. The power, we substituted in, it should be minus 0.971978. Anybody do check that calculation? All right. This is on Blackboard, by the way, right? So you don't have to. Oops. Yeah.
The last line.
Mm-hmm. Minus 2t, e to the minus 2t plus e to the minus 2t. Yeah. That minus 2 came from when I differentiated. We had to use this guy right here. When I differentiate this, you get that minus 2 pops down here, and I get the minus 2t to the minus 2t. Yeah.
Should it be 1 over minus 2?
No, that's when you're integrating. We're differentiating. Differentiate. All right, we're not doing the integrals. We're doing the different, almost all differential equations. Dr. Wooski. Wow. Dr. Woo. Mr. Helferty, we have ways to make you learn these things. Yes. And we'll be getting to derivatives. That's the next topic, which will be your final topic. All right. What? You got it? You okay? What? What? Nothing. Just teasing, man. All right, so when you crank that number out, you should get minus 0.1978. Got it? Okay. Now you may ask, how can power be negative? I can supply power and I can absorb power. Okay? In this case, it's supplying when you get a negative sign. And you'll get to this when you take your circuits course in physics and if you take electrical and computer engineering also. And for the final one, if we calculate 1/2 Li squared, you get around 98.9 millijoules. Okay? That's the actual energy that's being stored at t equals 1 second. Okay? Can I erase the right board? Everybody okay here? All right, let's do an integration problem, and then we'll move on to Most honorable differential equations. All right. This was an example. All right. Let me bring this guy down here. Now, again, you don't have to take these. These are on Blackboard for you, all right? I'm just going to go through this one, but then I want to go through one that has a little more detail. Yeah? The answers are on Blackboard. The stuff that I wrote here and here is not on Blackboard. The details, I just went through it with you. Okay? Good? Yeah. So I wanted to go through the details to show you how you get it. Okay? All right. Here what we're going to be given is the voltage across that inductor is according to that polynomial relationship there. And we want to find the inductor current, assuming that the initial inductor current is 1 amp. So we go to the relationship that we have for the inductor current in terms of its voltage, which is the integral. Oh, my mistake. In there, you see that integral? I should get my laser pointer out. That integral should be right there. Right? That should be V of t. All right? So on your notes, just make sure that you change that to V of t. All right? Like the new advanced laser pointer. Throwing darts, man. That's what Rodgers did against our defense. He threw a lot of darts. Whoops. All right. So now what we get is we substitute in. Again, this is a 200 millihenry inductor, so it's 1 over L, which is here. Now the lower limit of integration is from 0 because this is assuming that the time that we're working on here, t0, is 0. And we integrate the 3t squared, the 2t, the 4, and dt. And the 1 comes from the initial inductor current, I at 0. Okay? Comes from the initial inductor current. Now, again, this is on Blackboard for you, all right? So now when we integrate each of these three, okay, you're going to get a t cubed. And the 3 kids, all right, let me do it on the right-hand side board here for you. So we're integrating from 0 to t. 1 over 200 1 over 200 times minus 3 comes out to be 5. So this is 5. So we're integrating 3t squared plus 2t plus 4 dt plus 1. So that's what we're integrating out. So this is I of t. So now we break it up into each integral. We're going to have 5 times the integral of 0 to t, 3t squared dt, plus 5, the integral of 2t squared dt, plus 5, integral of 4 dt, plus 1. So I of t is going to equal 5. Now, t squared, that integral comes out to be 1, or I have 3, times 1/3 of t cubed evaluated between 0 and t, plus 5, 1/2 times 2. Let me just make that out a little bigger. Five times 2 times 1/2, and that's going to give me a t squared, or t cubed. This was t squared. This wasn't t. I have an extra t squared here. There we go. T squared. Evaluated that between 0 and t, plus 5 times 4, and that last one is just t. Integral from 0, and these are all from 0 to t. And we evaluate that between 0 and t plus the 1. Now we put in the limits of integration. So we're going to have 5 times t cubed plus 5t squared plus 20t plus 1. And that gives us our final inductor current. So this was integrating polynomials, okay? Integrating 3 polynomials. Yeah.
Which, in the first, when the equals, which one did you say was V instead of, did you just switch one?
Right there. Oops, almost got it.
So what was V?
That's v of t. It's the integral from 0 to t, and then I have I there. That should be a v of t. Okay. Anybody else? Woo-hoo! All right. All right, let's do one nice and long one, and then we'll go on to chapter 10. How's y'all doing in the midterm? What was the, did he give you an average? Didn't give you an average?
It's too depressing to talk about.
Come on. Curve? Like a slider curve? Really?
Throw to third base and it's a strike.
And it's a strike. Back, so it does like a 90-degreer. All right. I throw fastballs myself, all right? Fastballs. Bring on the heat. All right. Oh, let's see. That's just another. I want to get to the. I'll leave this one blank. You can go through that one. Ah, this is the one. All right. We have a voltage source tied to an inductor, and the voltage source is switching constant, plus 9, down to minus 9 volts, back to plus 9, down to minus 9. All right. So this is a switching power supply here. All right. And it's just doing what's just sending out these little pulse trains. Okay. For those of you that go into electrical and computer engineering, that's called pulse width modulation. Big way to control motors, servo motors, stepper motors, because all those motors, physically, a motor you saw the other day, I showed you a little video of a motor. What's it made out of? Induction coils. Stepper motors are beautiful. I mean, you can accurately control the position of them. All right, we use them in robotics all the time. So what we're doing here is we're going to fire that inductor up with a plus 9, then we're going to switch it to minus 9, then plus 9, then minus 9. All right. All right. Let's take. I'm going to move this up so I can use the middle board. There we go. All right. All right, so now what we're going to start off with, I work from left to right here, okay? All right, so we have, what we need to do is we're going to have to find the current. So now what we have is, let's first write out what the voltage is. V of t is equal to, oops. And we're going to work on each one of these time intervals. It's equal to plus 9 for 0 is less than or equal to t, which is less than or equal to 2. It's equal to minus 9 for 2 is less than or equal to t, which is, oops, I can't say equals there. Less than or equal to 4. It's plus 9, less than or equal to t, which is less than or equal to 6. And then it's minus 9 for 6 is less than or equal to t, less than or equal to 8. Okay? So that's what V of t is. Now let's first get the first time interval. What we're going to do, I think I assumed the initial conductor current was 0 here. Yeah. We're going to assume here that I at t equals 0 is equal to 0. We have to know this because we're going to use I of t is equal to 1 over L, the integral from 0 to t of V of t dt plus I at 0. We have to know this. So in this case, I didn't put it on the slides, but just write down that I of 0 is equal to 0. Okay? You have to know the initial condition. You have to.
I don't believe it's not written down as 0.
Just if it's on an exam or something like this, say, hey, look, I got to assume something, so just assume it's 0. Okay? It's the inductor is initially unenergized. Okay? All right. So let's start off. We're now going to solve this on the thing about these when you have to break up these time periods, just break them up. Don't look at all of them at once. We're only going to look at from 0 to 2. That's all we're going to concentrate on first. So now we're going to look at for 0 is less than or equal to t, which is less than 2. Can you guys see that with the light on? Is that okay? You're good? All right. All right, so now we put it in. I of t is equal to 1 over L. The integral in this, it's 1 over 500 times 10 to the minus 3. Integral from 0 to t. Now again, I could make this 2 here, but I'm just going to make it t, and then I'm going to substitute in t equals 2. All right, so here becomes, this is plus 9 dt plus 0 due to the original inductor current. Okay? Now 1 over 500, I think this comes out to be 2. This should be 2. You get a 2? So that's 2. And now I'm going to bring out, so I multiply that by the 9, and then I have the integral from 0 to t of dt. Okay? This integral comes out to be, 2 times 9 gives me 18. The integral ends up being t, and we evaluate it between 0 and t. Okay? And now what we're going to do is, I'm over on the right-hand board here, I'm going to write down the I of t. Now this is going to be valid for 0 is less than or equal to t, which is less than or equal to 2. That's what we're going to find. We're going to find the current over those 4 time intervals. All right. What's the integral of t? Oh, no, I mean, we got t here. So this is equal to 18 times t minus 0. Again, we're evaluating between the lower limit and the upper limit. So now I of t for the first time interval is 18t. And let's look at this anyway. Before I kind of jumped into the mathematics here. If I'm going to plot as a function of time the inductor current, and I have t equals 2, 4, 6, and 8. Everybody sign? Everybody good? Okay. Let's just graph this without going through all the mathematics first. Let's just kind of pull back a little bit. All right, so just let's take a look at this. On the first time interval, my inductor has no current in it, has no energy. I now throw 9 volts across it. What's going to happen to the inductor current? It's going to start increasing. How's it going to increase? I'm integrating a constant. I'm integrating a constant. So what is it going to become? Linear. 18t, right? So I know that this is going to start at 0, and it has to go like this to some point. Now I switch the power supply the other way. Boom, the voltage goes the other way. What's going to happen to the current? It's going to start drawing out the opposite way. And when I switched that voltage, it went to a constant, a negative constant. So now I'm at minus 9. I'm integrating minus 9, or I'm looking at the area under minus 9. What's going to be the slope? Negative. So this guy's got to start doing something like this. It's got to do that. Now, where it ends up at, I don't know. But now over this time interval, so this has got to go negative here. On the next time interval, I switch it back to positive. Boom. What's the slope going to be? It's got to start increasing linearly again. And then the other one, when I switch it to negative, it's got to go like that. So over this time interval, I have a positive slope. Here I have a negative one. Here I have to have a positive one. And here I have to have a negative one. So I can kind of like look and see before I even start the problem, just using my intuition and what I know what's going on here, I know that in the end I got to look something like that. All right? So now let's actually get into the details. So here, when we solve for I of t on this time interval from 0 to 2, what do we end up with? This curve right here is 18t. Now we go to the next time interval. 2 is less than or equal to t, which is less than or equal to 4. And now we have I of t is equal to 1 over L, which is 500, times 10 to the minus 3, the integral from 0 to t of minus 9 dt plus I at t. Oops, this can't be 0. This lower limit has to be 2. And I of t equals 2. Where do we find I at t equals 2? That comes from here. I at t equals 2 is right here, which happens to be 36. So I of t is going to be equal to, now again, 1 over 500 times 10 to the minus 3 is going to give me a 2. That gets multiplied by minus 9. And now we have the integral of t evaluated between 2 and t plus I at t equals 2, which is 36. This is minus 18 times t minus 2 plus 36. So I of t is equal to 8t plus, or minus, plus 36, right? So therefore, I of t is equal to minus 18t plus 72. So now I'm done on the interval from 2 to 4. So this curve here is minus 18t plus 72. That's that curve there. Is everybody okay on that integration? Good? All right? Now, we go to the next time interval. 4 is less than or equal to t, which is less than 6. I is equal to 1. The integral from 4 to t of plus 9 dt, plus we need I at t equals 4. Let's see, 18 times 4 is going to give me 72. So this number is going to equal, we get this from minus 18 times 4 plus 36, which happens to equal 0. All right, so I of t is equal to 2 times 9 times t evaluated between 4 and t. 18t minus 4. So now it looks like this curve looks like this. This goes down to 0, straight. This one over here is going to do this. We're going to do this. And then we're going to do that. Yep.
Are we always disregarding a higher value?
What do you mean disregard the...
Like, you say 4 is less than 2 and less than 6. Like, we didn't use the 6 at all.
Oh, yeah. I'll get to the 6. This relationship is good between this. So this is 18t minus 4. Okay? Right? And that's valid between 4 is less than t, which is less than or equal. I can get this. It actually comes from the physical principle of an inductor, that the inductor current cannot change instantaneously between one little time point and another. So right before I get to 6 and right when I'm at 6, it's still valid. All right? That's a very good point, though. It really is. The argument, when you get into calculus, you can make the little arguments a little bit more refined here. Okay? All right, and then we have the final one is we have I of t. Now this is for 6 is less than or equal to t, which is less than or equal to 8. I of t is 1 over 500, 10 to the minus 3, integral from 6 to t of minus 9 dt plus I at t equals 6. I at t equals 6 is going to be 36. And that comes from here, which is equal to 18 times 6 minus 4. I get it from that expression there. So this is equal to 2 times minus 9 times t evaluated between 6 and t plus 36. So it's minus 18 times t minus 6 plus 36. Can somebody give me 18 times 6?
108.
How much?
108.
So this is going to be minus 18t plus 108 plus 36. Add 36 to that. Looks like you get 140, right? No. 144, yeah. So this is minus 18t plus 144. And that's my last one. And that's it. That's all. That's everything there. All right. Hey, Homer, you got it right. Die. All right, we're good. So you can see the inductor starts at, it gets energy is pumped into the system, energy is taken out during the second time interval, energy goes back into the system, then energy comes out. All right? And that's it for integration. We're done. Yes, sir.
I think you made a mistake when you did T.
I never make a mistake. Ha! You gotta be kidding me. I woke up this morning. That was a mistake. I missed the Temple bus at 7 o'clock. Got there at 7:02, and they were out of here. I missed my swim this morning. No, I'm sorry. Go ahead. I'm throwing curveballs, man. All right? Go ahead. What is it?
You did negative 18 times 4 plus 36, and that's equal to negative 30.
Oh, you are correct, oh great one. Oh, let's see what we got here. Where'd that come from? I at t equals 4. I at t equals 4. Oh, I'm supposed to be using this, right? This should be 72. Sorry. Thank you. That's a 72 there. Yeah. Yeah, I do make a mistake. That's 72. Make sense? All right? Lunchtime?
Differential equation time.
Differential equation time. Woo-hoo! All right, we're done with the integration. No, seriously, any questions? We okay? Again, we're just applying, in this case, these integrations, okay? Yeah.
You always had like a linear, like, slopes for graphs. What kind of voltage would you put into something to make the current?
If I started, if these curves were now like this, if I can use, and in electrical engineering, we have function generators that can create those signals. Or now, if let's say I put into the system a ramp. Let's say it was ramping up and ramping down like this. Instead of square waves, those are square waves. These are ramps. If I now put in something like this, I'm now integrating a linear curve. What am I going to get? I'm going to get a polynomial. It's going to be a t squared. So you will get away from those linear relationships. Okay? When you start putting in something like that, the area under this now becomes quadratic. All right? All right, we got 8 minutes left. We're good. Can I erase the middle? Everybody okay? All right. All right, I loaded up onto your blackboard some slides for differential equations, so you'll see them under chapter 10. And let me just go dig them out of my. We've actually been doing differential equations already. I think I have a laser pointer here. Let me try to pull that. Come on in, wacky laser pointer. Huh? Battery dead. I have another laser pointer. Always have a backup. Redundancy in the system. Fail safe. Anybody see that little lander on the comet? Isn't that pretty wild? It bounced off though. Now it's got stuck in a canyon. The solar panel can't get any light. It just shut off. It went into sleep mode. You better not fall asleep there, pointer. Ah, there we go. All right, differential. Differential is exactly that. Things are moving at different rates, all right? Nothing's constant here. For mechanical engineering, you'll be taking statics. There's no derivatives in statics. Everything is static. It's not changing as a function of time. In dynamics, you will get differential equations because things are now moving. You got a motor rotating. You got gears that are going. In electric circuits, we got current and voltages that are changing as a function of time. Environmental engineering, you may have a pH sensor measuring pH that's varying as a function of time. Everything in differential equations varies with some independent variable. We're going to be using time as the independent variable. Well, we can use distance also as an independent variable also. Something's going to be moving, all right? And that's where we get these rates of change that constantly occur. Rates of change can be described mathematically as differential equations. That's the beautiful thing about it is. The nice thing about this math, you may say, oh, damn, what is it? It describes nature. And when we get a mathematical model, we can then start, instead of going and running experiments all the time on a nuclear reactor or whatever, you can use the mathematical models to start predicting how the system's going to work. Those models are usually written as some type of a differential equation. And whether you like it or not, MATLAB is becoming an industry standard on using models that are written in ordinary differential equations. So if you don't like MATLAB and you don't like differential equations, go to business, all right? Or go to social sciences. Because here, that's the language which we live in, all right? Seriously, that's the language. So if you don't want to get the language, no comprende, vaya con Dios, okay? Got me? All right? All right. Just, we want you here. But really, this is the stuff that describes how nature works. Yep. All right. Let's take this simple little leaky bucket. You know what? We're not going to get into the math. Let's just talk about this for a minute. I fill the bucket up. And then I take the spigot away. I open up a little spout at the end. What's going to happen? It's going to leak, right? It's going to leak. I mean, it's going to go. So what I'm saying is, if I graph the volume of water as a function of time, let's just say I graph. So I'm going to start off with, now we can do two things. We can look at the height of the water, or we can look at the volume of water. They're related because it's a big cylinder. I have a cross-sectional area. I know the height. I can calculate the volume. So in other words, let's just look at the height for now. I want to graph the height as a function of time. Not with that pen, I'm not. So if I start off with some initial height, 4 feet in there, we open up a valve, what's going to happen? It's going to decrease. Now it can decrease linearly. It can decrease exponentially. It depends upon the physics of how the fluid. It's got a certain viscosity. There's properties of the fluid. It depends on that little opening there. That opening could have some friction in it. We don't know, but we know it's going to decrease and eventually go to zero, right? Now, let's say I started at an initial height and I pour fluid in and I let the fluid out. So now the question is, what happens to the height? Well, it depends upon how fast the fluid's going out and how fast the fluid is coming in. If the volume coming in is equal to the volume going out, what's going to happen to the height? It's going to stay the same. In that case, I can start looking at it, saying, you know what, you started here, you're going to stay there. Now let's say I'm pouring it in, I'm taking it out, but it's going out a little bit slower and it's coming in. What's going to happen? It's going to start increasing, okay? So we've got these scenarios here, and it can increase. Again, I start at a certain height. It could go up like this, or it could go up exponentially. I don't know. We have to go to the physics of the system to figure out what it's going to do, all right? How that is going to, and again, everything, the independent variable here is time. Is time. So now what we're going to look at is what are the rate of change of things with respect to time. That's what we have to figure out. What is that rate of change? Okay? So we start off, again, the volume is equal to, we're right at 12:50. I'll let you guys go get lunch. See you guys on Wednesday.